Okay, so I don't know, Sean's not here, I don't think. Nope. So I'm recording this for Sean at least. All right, or for you to see it later. In the electrostatics packet, there's a page that says charge distribution. And there's a very important statement at the top. It says, when charge is placed on a conductor, charge quickly spreads to the surfaces. So the electric field inside the conductor is zero as a shielding effect. Let me draw something to show you what that means. So if you have like a three-dimensional like shell, just a round shell, and you happen to put charge on that shell, and it doesn't really matter if it's positive or negative, but let's just say that there are electrons. Those electrons wouldn't tend to clump up and all stay on one portion. Instead, because they repel each other, they will end up spreading out so that the distribution of those electrons, whoa, that was crazy. Oh, that's a mess. So that the distribution of electrons is the same all across the entire surface. Hold on, let me fix that. Hopefully that doesn't happen again. Oh, that's not good. I guess I can't go too far to the bottom on this thing. All right, let's try this again. There we go. So instead of those electrons all being clumped up on one side, they're going to end up being distributed more evenly all around the surface. They repel each other. Now, consider a place that's inside here. So if we pick a place that's like, you know, some point that's here, there is a field that's at that location that's as a result of the charge from each of them, but the charge inside the shell has a net charge of zero. And that effect is called the shielding effect. And sometimes in, actually a lot of times in wires, in electronic components, you might have a conductor itself. So the conductor is like a straight piece of wire. And then to prevent electromagnetic radiation from interfering with a digital or analog signal in the wire, sometimes the wire is shielded. And that shielding of the wire is oftentimes like another braided, wrapped wire that goes around it. This is a good illustration, but I'll show you what I mean here. Let me switch to a different program so that, let me get my mouse back. I lost my Safari browser. Doesn't really matter which browser. So for instance, coaxial cable that's used for cable TV, there's a conductor that's in the center. This is a good example. Yeah, that's okay. There's a conductor that's in the center, and that's this solid wire here. And then wrapped around it is this braided wire. That was kind of like what I was trying to illustrate. And it's called coaxial because this solid wire and then this stranded wire which wraps around it share an axis. That's all that coaxial cable means. So if you see the end of a coax wire, in order to like hook up a cable box, this is actually the physical wire that's inside the cable. And then to offer shielding from outside electromagnetic radiation, this braided wire section, which is wrapped around another insulator, that is electrically conducted or connected to the outside connector here. So when this connects to the chassis of a cable box, the cable box itself acts as a shield, and so does the braided wire that is around the center part. So anyway, sometimes on the AP exam, it'll say like, oh, you have a, like a circular thing like this, and it'll be like, here's the radius, it'll be like 0.5 meters, and then there are charges placed around that circle, a charge here, a charge here, charge here, and a charge there. And the problem will be like, what is the net electric field in the center of this object here. And you might be like, well, that one's pretty easy because from this location, there's a, if you put a positive charge here, it'd be attracted to this charge. So there'd be a force up. It'd also be attracted to this one. There'd be a force down. There'd be a force this way. There'd also be a force this way. So you'd be like, well, that's just zero. That's all you end up with. So that one's pretty simple. But then on the other hand, what if it were that you have a charge that's here, charge that's here, charge here, and a charge that's there? And the question may be, you're at some other position like this. And what's the net charge at that position? Well, you might be like, well, I've got an attraction toward this one. So there's a force that's to the right, or I'm sorry, to the left that's here. And it's quite large because we're relatively close to that charge. But then at the same time, there's an attraction to this one. But you know, that charge isn't very big, so the force isn't very large. And then there's a force that acts up this way, and there's a force that acts this way. And you might be like, ooh, well, maybe and actually the force that's in this direction and that direction are larger than this one. You'd be like, ooh, well, maybe the horizontal component of this one and this one, when those two are added up and added to this force, might be the same as this force. And your suspicion would be correct, that the net charge at all positions that are inside the, hold on, let me see if this will work. Oh, that doesn't work. Let me push this button. Oh, this works. That's pretty good. The electric field inside the conductor, or electric field inside of space, ends up to have a field of zero. There's another concept, and that's the concept of electric flux. So this equation here, hold on just 1 second. I gotta check on something real quick. All right, let me write this equation. So flux also means like to flow. All right, so here's the equation, and it says phi is equal to EA. This is the Greek letter phi. It's the uppercase Greek letter phi. It's actually in Greek pronounced phi, and it's usually made with a circle, and there's a vertical line that runs through it. There's a thing down at the bottom, a thing at the top. And this is the symbol for electric flux. And this is field strength. That wasn't good. Which you know has the unit Newton per meter, and then you have area, which is in like the unit meters squared, or Newton per coulomb, and you write Newton per meter, Newton per coulomb. So that makes the electric flux have the unit Newton meters squared per coulomb. So here's what electric flux means. Consider a point charge. And from that point charge, we have a field, and it's a positive charge. We have a field which extends from that charge. And I'm going to draw some field lines extending from it. I'll draw 8 of them. And then consider that the field strength is different at different positions. The field strength is quite large when you're close, and it's much less when you're further away. Now consider a couple different areas. So consider an area like this. So this is a 2-dimensional area through which the field lines extend. When I'm close, we have a relatively high field strength. There's 3 field lines extending through that area when I'm relatively close to it. So here we have a large field, and therefore you get a relatively large flux. When we consider that same area at a much greater distance, so now I'm out here at a larger distance, the same amount of area, there's only one field line that extends through it. And even if I were to move this area much closer down, we have a much smaller field strength for like the same area. Well, I don't really mean to say large. Well, it's the same area, so we have a relatively, oh, I'm not even awake yet, relatively small flux. The same kind of concept applies with photonic incidence upon a surface. So for instance, if you consider a surface and you have a light and you shine that light down on the surface so that the rays are very perpendicular to the surface, you have a certain amount of intensity of light here that's relatively high. That intensity is large because the surface area is relatively small. If instead you take that same light and shine it down at a smaller area, a smaller angle like this, then the number of rays that pass over a certain area has been reduced. In other words, those same 4 rays, I'll do it like this. So when the 4 rays are incident normal to the surface, we have those 4 rays on a relatively small surface, or for any amount of surface area, there's a high flux. In this case, if you pick that same surface area, so here if that surface area is represented by this distance, we have 4 lines, but now that same surface area represented by like this red distance may only have 2 lines. So there's a smaller flux or a smaller incidence of light per amount of surface area. Flux used to be quantitatively assessed on the AP exam before the AP Physics 2 exam. Now it's assessed more qualitatively, and that flux is equal to the field strength times the area. So if you have a very high field strength and a very large area, that gets you a very high flux. Flux like flow, like there's a number of field lines that extend through the surface. Anyway, you can read more about that in chapter 15. There's a thing here about Coulomb's law and forces acting in 2 dimensions for Coulomb's law, and net forces and net fields acting at points relative to other points, and we did problems like that. So anyway, in that packet, and it begins on page, I don't know if the pages are numbered, but in that document, there are some multiple choice questions. And let's see, there's one. Yeah, there's a 12, 13, 14. Yeah, there's 16 multiple choice questions. And those 16 multiple choice questions are multiple choice questions that appeared on recent AP exams. Following that, there is an open-ended problem that's about some position P relative to 2 other charges. And these are nearly identical to problems that were in the first portion of the problems in chapter 15 in the textbook. So there's actually only one open-ended problem. The chance of there being an open-ended problem related to fields and forces is not particularly large on the AP exam, but the conceptual questions and multiple choice questions, there's a much greater probability. If there's going to be something about electric fields and forces on the AP exam and the open-ended problem, the open-ended part, it's probably going to be part of a problem related to maybe capacitors or electric circuits in some kind of way, which is what we're going to study like pretty soon. Okay. All right, so here's the plan. I didn't put the plan for the week on the site yet, but what I want you to do is if you go into the chapter 15 folder, that NIMSY electrostatics packet, I want you to work through the multiple choice questions, and tomorrow and Wednesday, I'll take questions about those and we can go over them. I'll write the thing for the week and I'll include that in there. The other thing that I can point you to that's a help is the problems on page 524. I recorded solutions to a bunch of those, and there are some more problems that I want to also put on there. And I'll put those in the plan for the week. But here on my YouTube channel, there's problem 1. Well, they sort of came out of order because when I batch uploaded them, whichever one's the shortest one goes up first. You can even see that in time. It's like 1 minute and then 2. Oh, these 2 are switched. 4, 5, 7, and then 8 minutes. So I put problems 1 to 5, 7, and 10 to 12. So I don't know, numbers 2 and 4 didn't show up. 7 and 10 didn't show up. I need to figure out where those went. But anyway, the problems that I wrote on the board, page 524, 1 to 5, 7, and 10 to 12, all those solutions will be here. And then I'll put some additional solutions to problems related to electric fields. All right, so that should get you started. I was, well, hoping / not hoping we'd be back in person. Hoping we'd be back in person so you could have a test on paper and pencil, but not hoping we'd be back in person because this Rona's got us good. So I'm gonna have to write an online test, which takes me quite a while to do. And I'd like us to do that this week. So I want to actually shoot for, well, I'll open it on Thursday. Well, I don't know. Maybe I'll just open it for Friday. And then, I don't know. I got to think about it. I really wish I knew what we were doing next week. But yeah, maybe I'll open it for Thursday. So how about we do that? I'll plan on writing and then posting a test that you can do online. So we'll do it online anyway, and some students are remote anyway, so they have to do it online. So I'll post a test for electric fields on Thursday, and you still have to check in. So that's the school's policy, is that you have to check in every class, and then you can work on that test. So really everything is just from chapter 15. The NIMSY pack is actually very comprehensive. It has all the stuff about electric fields and forces, and check to see if the sound is working. Has everything about electric fields and forces and some good example problems. I don't know if my sound is on right now. Maybe I don't have my speakers plugged in. There we go. Metabolism and cognitive function of brain cells in an organoid mind. All right, I had I installed a new program to be able to deal with sound, but I haven't got it figured out yet. We'll see. All right, so do you have any questions or thoughts about anything before I set you loose? None. Okay. So in the chapter 15 packet, look for the NIMSY electrostatics thing. Jaden wrote nope. At least Jaden's paying attention. Everybody else just like logs in with their phone, goes back, takes a nap. It's funny is in some of my classes, like we'll get going and about 30 minutes in, I'll be like, okay, we're done for the day. And then I'll notice like 4 or 5 people are like still there. And then like about 3 minutes after that, one of them will say, what's going on? Am I supposed to still be here? I'm like, I let you go like 4 minutes ago. They're like, oh, I had my sound off. I was in a different room. So I don't know. It's mostly sophomores. They don't really have their act together. It's always rough. Yeah, I know this is rough. This is tough. I mean, we're trying to have some kind of consistency and try to do things sort of the same. Yeah. All right. So work on that NIMSY packet and try to get through the multiple choice things. And I'll take questions about those first thing tomorrow. But then I want to go over that with you tomorrow and Wednesday. And then that should get you ready. So if that's it, you can dip and catch it tomorrow morning, bright and early, 8:40 or 7:40.
All right.
See ya.
Thank you, Mr. Flint.
See ya.
See ya.
See you, Flint.